And so just to recap, we're wondering how acceleration is changing with respect to time when we have two functions that sit between acceleration and time. And here's our problem. We have acceleration that is a function of angle, and we have an angle that is also a function of time. And so there's two functions together, chained together. And so there we go, angles changing with time. And so we want to use calculus to find out how acceleration is changing with respect to time. So if you recall, there's my relationship between acceleration and angle. And now this is just made up, and you'll notice that I'm probably lying here. But here's my relationship between angle and time. I'm saying that angle is increasing as some quadratic function of time. So when I come up with a combined statement, I know that acceleration is 9.8 times the sine of the angle, and I know that angle is equal to 2 times time squared. So if I want to express this as acceleration as a function of time only, there's my combined expression. But if you recall, what we're really trying to find out is how acceleration is changing with respect to time. First thing I'm going to do is try and find out the relationship for how acceleration is changing with respect to theta. For the time being, I'm just going to let the expression be a equals 9.8 times the sine of theta, and I'm going to keep in the back of my mind that theta is equal to 2 times time squared. So let's go ahead. dA d theta, fairly straightforward. We have a constant, so we don't have to worry too much about the constant, 9.8, and the derivative of sine is cosine, and we can just leave the inside as it is for now. So there's dA d theta, 9.8 times the cosine of theta. Okay, now we want to find the derivative of theta with respect to time. So I know that theta is 2 times time squared, and what I need to find out is the derivative of theta with respect to time. And so I can just use my power rule and my constant rule on this expression. d theta dt is equal to 4 times time. So there, I have dA d theta, I have d theta dt. Now I'm all ready to go ahead and find dA dt. And so straightforwardly enough, dA d theta times d theta dt is equal to 9.8 times cosine of theta times d theta dt, which is equal to 4t. And now I'm ready to make my substitution in theta, because I know theta is equal to 2t squared. So there's my complete expression for dA dt. And of course I can refine this a little bit on the left-hand side. There. dA dt is equal to 9.8 times the cosine, 2t squared, times the derivative of the inside, 4t. And just compare that to the original expression, a equals 9.8 times the sine of 2t squared. You'll see that actually the chain rule isn't all that intimidating in the end.